Hey Midnights. Thank you for listening to Midnight Overdose. Where are you listening from? Our next topic, Exoplanet K2-18b. The breathtaking proliferation of exoplanet discoveries in recent decades has dramatically expanded the canvas of our cosmic imagination, transforming the once fanciful notion of other habitable worlds into a tangible pursuit. Among the myriad of exoplanets catalogued, K2-18b, a super-Earth orbiting a red dwarf star some 124 light-years away in the constellation Leo, has emerged as a focal point of intense scientific inquiry and public fascination. Its intriguing properties, particularly its placement within the habitable zone of its star and the tantalizing spectroscopic evidence of water vapor and carbon-bearing molecules in its atmosphere, have fueled a compelling debate. Could this distant world truly be a mirror of Earth, a potential cradle for extraterrestrial life? The journey to understand K2-18b began quite recently. K2-18b was first discovered in 2015 by the Kepler Space Telescope during its K2 mission, following its initial highly successful planet-hunting phase. The discovery utilized the transit method, where astronomers detect a periodic dip in the host star's brightness when a planet passes in front of it from our vantage point. This subtle dimming provides crucial information about the planet's radius and orbital period. Subsequent observations using radial velocity techniques, measuring the wobble in the star caused by the planet's gravitational tug, allowed for the determination of K2-18b's mass. These early measurements established K2-18b as a super-Earth. At the heart of K2-18b's allure is its undeniable presence within the habitable zone of its parent star, K2-18. This region, often colloquially termed the Goldilocks zone, defines the orbital range where a planet could theoretically maintain liquid water on its surface, an absolute prerequisite for all known forms of life. K2-18, a cool M-type red dwarf, has a lower luminosity, around 0.0234 solar luminosities, than our Sun. This lower energy output means K2-18b can orbit much closer to its star and still experience temperatures conducive to liquid water, estimated to be in a range that could support such conditions. The excitement surrounding K2-18b reached a fever pitch with the direct detection of water vapor in its atmosphere. Initial observations in 2019 by the Hubble Space Telescope provided strong evidence for water using transmission spectroscopy. This technique, where light from the host star passes through the exoplanet's atmosphere during a transit, allows specific wavelengths absorbed by atmospheric molecules to reveal their composition. This marked a landmark discovery, as it was the first time water had been found in the atmosphere of an exoplanet within its star's habitable zone. More recently, the James Webb Space Telescope, with its unprecedented infrared sensitivity across a broader wavelength range, has delivered even more detailed insights. JWST observations in 2023 detected clear absorption features consistent with abundant carbon-bearing molecules, including methane and carbon dioxide, in K2-18b's hydrogen-rich atmosphere. The relative abundance of these molecules, coupled with a notable shortage or non-detection of ammonia, strongly supports the Hycean world hypothesis, a theoretical class of exoplanets characterized by a substantial hydrogen-rich atmosphere overlying a deep, planet-wide liquid water ocean. These Hycean worlds are thought to be common around red dwarf stars and offer a potentially expanded habitable zone due to their larger sizes and extended atmospheres, making atmospheric characterization more feasible. Furthermore, the JWST observations have hinted at the possible detection of dimethyl sulfide or dimethyl disulfide in K2-18b's atmosphere. This potential discovery is particularly significant because, on Earth, DMS is predominantly produced by marine phytoplankton and certain bacteria, giving rise to the characteristic smell of the sea. While other non-biological sources of DMS have been identified, for example, volcanic activity, the strong association with biological processes on Earth makes its potential presence on K2-18b a tantalizing biosignature, a chemical byproduct that could indicate the presence of life. The prospect of an alien ocean teeming with microorganisms producing such a gas, much like Earth's phytoplankton contributing to our atmosphere, is a powerful driver for continued investigation. For context, on Earth, DMS has a very short atmospheric lifetime, implying continuous replenishment if detected in significant quantities. The reported concentrations for K2-18b are significantly higher than Earth's, which, if confirmed and attributed to life, would require a robust biogenic flux. Biosignatures are crucial in astrobiology because they represent remotely detectable indicators of past or present biological activity on a planet. In the search for extraterrestrial life, directly observing alien organisms is currently beyond our technological capabilities. Therefore, Scientists rely on indirect evidence, primarily by analyzing the chemical composition of exoplanet atmospheres. The core idea is that life, through its metabolic processes and interactions with the environment, can leave a discernible chemical imprint that is unlikely to be formed by purely abiotic, non-biological, geological or astrophysical processes. They are important because they offer the closest we've come to direct evidence for life, help prioritize which worlds to study further, broaden our understanding of life's diversity, and can trace planetary evolution. Examples of well-known biosignatures include oxygen in ozone, methane in disequilibrium with oxygen or carbon dioxide, nitrous oxide, and methyl halides. The primary challenge in detecting biosignatures is distinguishing true biological signals from false positives, abiotic processes that can mimic biogenic signatures. This requires a deep understanding of planetary geochemistry, photochemistry, and stellar influences. The detection of DMs on K2-18b, while exciting, is still undergoing rigorous verification to rule out non-biological explanations. This highlights the rigorous scientific process of questioning and re-evaluating findings. The proposed evolutionary path of K2-18b is still a subject of scientific modeling and debate, but it likely differs significantly from Earth's development. Given its bulk density, K2-18b is thought to possess a solid core, likely rocky or icy, enveloped by a substantial volatile layer. Early in its formation, K2-18b would have accreted a significant amount of hydrogen and helium from the protoplanetary disk, likely retaining a thick primordial atmosphere due to its substantial mass and the relatively high gas density in its formation environment. Unlike Earth, which outgassed its secondary atmosphere primarily through volcanic activity, K2-18b would have developed with a dominant hydrogen-rich envelope from the outset. As the planet cooled over millions to billions of years, a global liquid water ocean could have condensed beneath this dense hydrogen atmosphere, supported by internal heat and stellar insulation. The high pressures within the planet's interior could lead to a layer of high-pressure ice, for example, Ice 7 or Ice X, between the liquid ocean and the rocky core, further differentiating its structure from Earth's. The planet's large size and deep atmosphere imply a more stable climate than smaller, less massive planets might possess, potentially allowing for the long-term existence of liquid water. However, the exact interplay between the deep interior, the high-pressure ice layer, the liquid ocean, and the hydrogen atmosphere is complex and actively being modeled. K2-18b stands in contrast to other potentially habitable exoplanets identified over the years, highlighting the diversity of conditions that might support life. For instance, the TRAPPIST-1 system offers 7 Earth-sized planets, 3 of which, TRAPPIST-1e, F, and G, reside within the habitable zone of their ultracooled dwarf star. These planets are roughly Earth-sized and are prime targets for atmospheric characterization. However, unlike K2-18b, the TRAPPIST-1 planets are thought to be rocky and possess thin atmospheres, potentially making them more susceptible to the intense flares from their host star and raising concerns about long-term atmospheric retention and the presence of liquid water. The close proximity of these planets to their star also means they are likely tidally locked, potentially leading to extreme temperature differentials, though thick atmospheres could mitigate this. Another famous example is Proxima Centauri b, discovered in 2016 and orbiting the closest star to our Sun. It is also within the habitable zone. However, Proxima Centauri, a red dwarf, is known for its frequent and powerful flares, which could be detrimental to a thin atmosphere and surface life. Unlike K2-18b's proposed Hycean nature, Proxima Centauri b is expected to be a rocky planet, making atmospheric escape a more critical concern. Kepler-186f, discovered in 2014, was the first Earth-sized planet found in the habitable zone of another star. It orbits a red dwarf star, Kepler-186, and is about 1.1 times Earth's radius. While it shares a similar size to Earth, its host star is cooler and dimmer than the Sun, meaning Kepler-186f receives less stellar flux. Its atmospheric composition is still unknown, but its size and orbital position make it a compelling Earth-like candidate. LHS-1140b, discovered in 2017, is another super-Earth orbiting a red dwarf star, LHS-1140, in its habitable zone. This planet is notable for orbiting a relatively quiet M-dwarf, which might be less prone to severe flares, potentially offering a more stable environment for a thick atmosphere and liquid water. These comparisons underscore that habitability is a broad concept, encompassing a spectrum of planetary characteristics. K2-18b, as a Hycean world, offers a novel avenue in this exploration. Its thick hydrogen atmosphere, while shielding a potential ocean, also presents challenges for understanding the specific conditions at the ocean's surface, such as pressure and temperature, and the potential for complex life. However, the path to definitively declaring K2-18b a life-harboring world is fraught with scientific challenges and inherent uncertainties. K2-18b is not a direct analog to Earth. The nature of M-dwarf stars, while offering a larger habitable zone due to their longevity, presents specific challenges. Red dwarfs, despite being smaller, are often more magnetically active than Sun-like stars, prone to frequent and powerful flares that emit intense X-rays and ultraviolet (UV) radiation. Such high-energy radiation, particularly in the extreme ultraviolet range, could drive significant atmospheric escape over billions of years, potentially stripping away lighter elements like hydrogen. While the Hycean model posits a thick hydrogen atmosphere that could shield an underlying ocean, the long-term stability and resilience of such an atmosphere against sustained stellar bombardment remain areas of active research. Another significant consideration is tidal locking. Planets orbiting close to their stars, like K2-18b, are often tidally locked, meaning one side perpetually faces the star while the other remains in eternal darkness. This could lead to extreme temperature differentials across the planet, with a perpetually scorching day side and a freezing night side. While theoretical models suggest that a thick atmosphere and a global ocean could help distribute heat and moderate these extremes through strong atmospheric and oceanic circulation, the exact climate dynamics and the viability of life in such a highly contrasted environment are still speculative. Furthermore, the interpretation of the spectral data, particularly the potential DM's detection, is subject to ongoing scientific scrutiny. Some researchers suggest that the detected signals might be noise or could be attributed to other common organic compounds like ethane, which has a similar spectroscopic signature to DM's and can be produced abiotically. The statistical significance of the DM's detection is also debated, with the initial research paper stating it is at the lower end of robustness typically required for scientific evidence. As Sarah Seeger, a planetary scientist at MIT, cautioned in response to the early findings, with thousands of exoplanets in view, the temptation to overinterpret is strong, and some are jumping the gun. When it comes to K2-18b, enthusiasm is outpacing evidence. Resolving these ambiguities will require more extensive and precise observations from JWST, accumulating higher signal-to-noise ratios and allowing for more robust atmospheric modeling and photochemical simulations. Given its unique characteristics, human habitation on K2-18b, in any conventional sense, appears highly improbable with current and foreseeable technology. The primary obstacle for human survival lies in its proposed Hycean nature, characterized by a crushing atmospheric pressure and an unbreathable composition. Even if a vast, liquid water ocean exists beneath the hydrogen-rich atmosphere, the sheer weight of this massive hydrogen envelope would create atmospheric pressures at the surface, or rather, at the interface with the ocean, that are estimated to be hundreds or even thousands of times greater than Earth's sea level pressure. To put this into perspective, even at the deepest known part of Earth's oceans, the Mariana Trench, pressures reach about 1,100 bars, a depth where specialized submersibles are required for exploration. On K2-18b, unprotected humans or conventional spacecraft would be instantly crushed. Moreover, the atmospheric composition, dominated by hydrogen with significant amounts of methane and carbon dioxide, is entirely unbreathable for humans. Our bodies are evolved to metabolize oxygen, not hydrogen or methane. Attempting to breathe such an atmosphere would lead to rapid suffocation and hydrogen narcosis. Even if the pressure could somehow be managed, terraforming K2-18b to create a breathable atmosphere, primarily nitrogen and oxygen, would be an engineering feat of immense and unprecedented scale, requiring technologies far beyond our current capabilities to either remove vast quantities of hydrogen and carbon compounds or synthesize breathable gases for an entire planetary body. Furthermore, the absence of significant free oxygen, which is a product of photosynthesis on Earth, means there would likely be no protective ozone layer in K2-18b's upper atmosphere. This leaves the surface, the top of the ocean, exposed to potentially harmful levels of stellar radiation, including X-rays and ultraviolet light from its parent red dwarf star. Such radiation could be detrimental to terrestrial life forms. The exact temperature conditions at the ocean's surface are also uncertain. While K2-18b is in the habitable zone, models suggest a wide range of possibilities, from frigid to very warm or even hot. Some extreme models propose a scenario where a supercritical water ocean might exist. In this state, due to extreme temperature and pressure, water behaves as a supercritical fluid, a phase where the distinction between liquid and gas disappears. Such conditions are not conducive to life as we know it. Even if a liquid water ocean exists, its chemical conditions, for example, pH, salinity, availability of essential nutrients, presence of toxic compounds, are unknown and might not be suitable for terrestrial life or capable of supporting an ecosystem that humans could integrate with or even safely interact with. In essence, K2-18b represents a fascinating laboratory for understanding the diversity of potentially habitable worlds and the limits of life, but it is not a candidate for direct human colonization or settlement. Any human presence would be confined to highly advanced, robust, and self-contained habitats or buoyant atmospheric platforms, essentially simulating terrestrial environments within the extreme alien conditions. This kind of floating city concept, while intriguing for gas giants, faces even greater challenges on a Hycean world where the atmospheric density and pressure gradients are so extreme. Such a prospect pushes the boundaries of engineering to its absolute limits and remains firmly in the realm of theoretical future capabilities rather than near-term feasibility. For those interested in pointing a telescope towards K2-18b, it's important to remember that K2-18b is a very distant and faint exoplanet, not visible to amateur telescopes or even most professional ground-based observatories directly. We detect it indirectly by observing its star. The star K2-18, also known as EPIC 201912552, is located in the constellation Leo. Its celestial coordinates are: right ascension, RA, 11 hours 30 minutes 14.51774 seconds. Declination, DEC, plus 07 degrees 35 18.2553 inches. These are the coordinates you would use to point a professional astronomical telescope. The star itself is a faint red dwarf with an apparent magnitude of about 13.50, meaning it's well beyond the visibility limit of the naked eye, which typically goes to about magnitude 6. Even with a large amateur telescope, you would likely only see the faint star, not the planet itself, as the planet is too small and too close to its much brighter host star to be resolved. Dedicated professional observatories like the Hubble Space Telescope and the James Webb Space Telescope are capable of studying K2-18b's atmosphere by analyzing the subtle changes in the star's light as the planet passes in front of it, a transit. These observatories utilize highly sensitive instruments that can pick out the tiny spectral fingerprints of gases in the exoplanet's atmosphere. For JWST, there are typically only about 4 transit opportunities observable each year due to the star's position in the sky and the planet's orbital period. Now, regarding travel time to K2-18b, this is where the vastness of space truly becomes apparent. K2-18b is located 124 light-years away from Earth. A light-year is the distance light travels in one Earth year, which is an incredible distance, about 9.46 trillion kilometers or 5.88 trillion miles. This means that the light from K2-18b that we see today left the planet 124 years ago. Humanity's fastest spacecraft to date is NASA's Parker Solar Probe, which reached a record-breaking speed of approximately 192.22 km per second, or about 692,000 km per hour, 430,000 miles per hour, as it swoops close to the Sun. However, this incredible speed is achieved through gravity assists from the Sun and is not sustainable for interstellar travel in a straight line. This calculation, a journey of nearly 200,000 years, highlights that current technology makes interstellar travel, especially to planets like K2-18b, entirely beyond our reach. Even to reach the closest star system, Alpha Centauri, about 4.24 light-years away, would take tens of thousands of years with current propulsion methods. For K2-18b, we're talking about a multi-generational journey that would span hundreds of thousands of years, far exceeding any human lifespan. This immense travel time is why the search for biosignatures through remote observation is so crucial. Direct exploration of these distant worlds remains a dream for the very distant future, perhaps requiring breakthroughs in propulsion technology like warp drives or faster-than-light travel, which are currently theoretical. Given the scientific information we have about K2-18b, particularly its classification as a Hycean world with a hydrogen-rich atmosphere and a potential deep liquid water ocean, any possible life forms would likely be vastly different from what we typically encounter on Earth. We would need to consider several key environmental factors for such life. The most significant challenge for life on K2-18b is the immense atmospheric pressure. Earth's deepest ocean trenches host life, called pizophiles or barophiles, that can withstand pressures over 1,000 times that at sea level. On K2-18b, the pressure at the ocean surface could be hundreds or even thousands of times greater than Earth's sea level. Life forms would need incredibly specialized cellular structures, unique biological molecules, like piezolites, and specific ways to process energy to prevent their delicate biological machinery from being crushed or destroyed. Another major factor is the hydrogen-rich atmosphere. Life on Earth primarily breathes oxygen. K2-18b's air is mostly hydrogen. This strongly suggests that any life on K2-18b would be anaerobic, meaning it would not require oxygen and would likely use hydrogen for energy. On Earth, we have many anaerobic microbes, including methanogens, tiny organisms that produce methane by using hydrogen and carbon dioxide, and hydrogen-eating bacteria, which thrive in places without oxygen, like deep-sea vents. K2-18b's environment would be an ideal home for such hydrogen-breathing life. The presence of a vast, deep ocean is a key feature. This suggests that any life would be almost entirely aquatic. The ocean could be incredibly deep, possibly spanning thousands of kilometers, with layers of high-pressure ice potentially separating the liquid water from the solid core. This deep, dark environment would strongly favor life that doesn't rely on sunlight for energy. The detection of methane and carbon dioxide in the atmosphere, along with the fascinating hint of dimethyl sulfide, gives us clues about how life might get energy. On Earth, methane is made by some microbes and consumed by others. So, its presence could mean a living system that produces methane, similar to what was common on early Earth. Carbon dioxide is a basic building block for carbon-based life. If DMS is truly a biological signature, it suggests life involved in sulfur cycles, similar to certain ocean organisms on Earth. Since a thick atmosphere would block most sunlight from reaching the ocean, any life would almost certainly be chemosynthetic, meaning it would get energy from chemical reactions rather than light. Possible energy sources could be geothermal vents on the ocean floor, which would provide chemical gradients for life to exploit, or chemical imbalances between the hydrogen-rich atmosphere and the ocean itself. What would this life look like? It would almost certainly be microbial. The extreme conditions of high pressure, lack of light, and unique chemistry would make complex, multicellular organisms like animals, plants, or fungi highly unlikely. Life would likely be made up of simple, single-celled organisms, similar to bacteria and archaea found on Earth. These organisms would need to be incredibly adaptable to high pressure, perhaps having squishy cell structures to avoid being crushed. Their proteins would need special structures to work under such extreme conditions. They would perform various chemical metabolisms, using hydrogen, methane, carbon dioxide, and sulfur. We might find organisms that eat hydrogen gas directly, or those that produce or consume methane, or those involved in sulfur transformations. Life could exist throughout the deep ocean, but might be concentrated around underwater vents or in specific zones within the ocean. In conclusion, K2-18b stands as a testament to the extraordinary diversity of exoplanets and a vanguard in the search for life beyond Earth. Its relatively recent discovery in 2015 set the stage for its ongoing characterization. Its location in the habitable zone, coupled with compelling evidence of atmospheric water, methane, carbon dioxide, and the tantalizing possibility of DMS, paints a picture of a Hycean world with a potentially vast liquid ocean. While the challenges of stellar activity, tidal locking, the precise interpretation of atmospheric data, the daunting prospects for human habitation, and the immense travel times necessitate cautious optimism, K2-18b represents a crucial and exciting testbed for our understanding of planetary habitability and evolution. The continued and future observations of this remarkable exoplanet promise to revolutionize our knowledge of exoplanet atmospheres and bring us closer to answering one of humanity's most profound questions: are we alone in the universe? The echoes of Earth and this distant super-Earth continue to resonate, beckoning us to look closer and dream bigger.